All right, everybody. Time to examine what this language of M4 is from last time. It's really hard. So when you get a really hard machine like this, the thing to do is to go ahead and list 10 strings in the language of the machine and 10 strings not in the language of the machine, and see if you can start to parse out some common patterns. Now, the key to this one is that the zeros and ones are actual pieces of binary. And so I've listed out some strings that are in the language and some that aren't, and then converted them into decimal so they're a little easier to think about. And when you do that, what you find is a common pattern that is a little more obvious over here, except for the empty string, perhaps. And there's something, also different over here. I didn't get all the way to 10, but you get the gist. So the common pattern is that this stuff over here on the left that the machine accepts are multiples of 3. And what you'll see if you investigate this deep enough is that these states are actually just modulo 3 states. So if you have a binary number that is a multiple of 3, you'll end up back here. If you have a binary number that is 1 mod 3, meaning if you divide by 3 and you're left with 1 left over, 1 remainder, then you'll end up here. And if it's 2 mod 3, then you'll end up here. So like the binary number 2, right? If you take 2 and you divide it by 3, you get 0 with a 2 remainder, right? It's 2/3 or something like that. So 1, 0 is the number 2, and it ends up here. What else? 5. 1, 0, 1, right? So that is the key to this thing. And like I said, these machines are really good at modular arithmetic. This is a DFA that can literally give you the modulus of any length binary number, right? It's not constrained. You just start spitting numbers, and as soon as you stop, it will tell you what the modulus of that thing is. And it only has to keep 3 states to figure it out, which is super amazing. I think it's super cool. If you're thinking of decimal, there might be even like better systems too, right? When you think of a number like 50, you can immediately tell it's divisible by 10. And there are some other tricks like that that might exist if you dig deeper. So the language of M4, I'm going to say, is the empty string and all binary strings divisible by 3. That's how I'm going to describe it. All right, so M4 settled. What we're here today to talk about are NFAs, so non-determinism inside our finite autonoma. So last time we said our transition tables all had to be really clean, but they don't have to be. We can have non-determinism, which is a way to make guesses. So here's our first bit of non-determinism, which is, what if I just don't specifically tell you where everything goes? And we talked about that at the very end last time. So like, hey, isn't Y supposed to be going to some trap state here so that I can fall off and die? And the answer is yes. You should fall off this machine and that route should die. But in a non-deterministic finite autonoma, we're allowed to make those kind of guesses or absences in our state machines. So that is an example. This machine here is an example where we can fall off the machine in a bunch of different places because we never said what happens on this symbol Y. So NFAs can do that. NFAs can also make guesses for which direction they want to go. So you can have multiple transitions on the same input. That's cool. A lot of times you'll see this because you want to make a guess as to which machine you're actually following, and it's an or statement, so you can be following one machine or the other. So if you pause this video and you try to figure out what this machine is, and then you try to figure out what this machine is, pretend they're 2 different machines, and then you or your answers together, then you'll have kind of the language of that bigger machine. Another example of guesses or parallelism in NFAs that is allowed are empty string transitions. So you can literally say, hey, I know I'm in this state, but I want to be in this state for free. And usually this happens because you are automatically constructing machines from individual parts. So usually this happens because of algorithmic development of finite autonoma in some way. You invent some algorithm that creates the finite autonoma, and you need to glue some pieces together or make a loop happen by gluing some pieces together. And so you'll see empty string transitions come out of that. In specific, NFAs are great for helping you start to learn how to build languages that have descriptors like language that begins with these symbols or contains these symbols or ends with these symbols, because they all can throw away the pieces that you don't need or make guesses where you need them. So let's do some examples of those. So here's some examples of NFAs that begin with 0, 1. So you can just literally worry about keeping track of the 0, 1. Once I know that it begins with 0, 1, then I stay here forever and I never leave. And I don't even have to consider what happens on these other transitions here. Begins with is pretty easy for DFAs too, so maybe this is an easy one. How about ends with? This one is really cool. I can just make a guess that I'm supposed to stay in the start state until I see the 0, 1 that gets me to the accept state. That actually is a lot easier to write with an NFA than it is with a DFA. It's pretty cool. And then you can do this with any ends with. You know, if it said ends with 0, 1, 1, 0, then you would just have more states over here. This would be the accept state instead of this guy right here. And bam, you have ends with 0, 1, 1, 0. Super cool. And then the other one is contains 0, 1. This one you have to put the loops on both ends. So you put a loop here, and then you say, hey, if I ever see this 0, 1 that I'm looking for, then I know I've gotten to the accept state and I never want to leave. Very, very amazing. Very cool stuff. So let's look at some of these differences here. And a little more formally. Oh, you just get a giant notability screen. That's amazing. So let's look at some of these differences a little more formally. Okay. So in a DFA, you kind of have one path through the machine instead of multiple paths, and all of your options are fully determined for you. You know where you're going at every point in time. There's no confusion there. With an NFA, you can fall off. You might have multiple paths, like when you had that first one, or you had those empty string transitions, and it makes things a little confusing. So let's look at the formalism. So they both have a finite set of states. That's this Q here. That's not different. NFAs might have less states than a DFA that does the same language, but that's okay. They both have a finite list set, the finite set of accept states. That seems okay. Those accept states, of course, come out of the Qs here. They both start with some state. They have a single start state. In the NFA, you might have these empty string transitions that make it feel like you start in other states. We'll handle that later. They both have a finite set, which is the alphabet. That is also true over here in the NFA, although you will often see it listed like you see over here, which is as sigma with a little epsilon here. And that means sigma union with epsilon. In other words, we understand that epsilon is not part of the alphabet, but we can have empty string transitions. That's what that's about. And that comes up when we talk about the transition function, which is down here. So over here, we said the transition function was, hey, if I'm in a state and I know what the input symbol is, that tells me exactly what state comes next. That's the deterministic finite autonoma. But over here, if I'm in a state, I might see some input symbol or I might see the epsilon. And what it leads me to is any number of states, including perhaps no state, like I might fall off and die, right? So this is amazing because this is amazing for several reasons, one of which is going to come up in another video, but one of which comes up right now. But the biggest part of it is I can still build this table, which is amazing. I can list my input alphabet and epsilon over here. I can list my set of states over here. The difference in this table is instead of these being single states, they're now sets of states, which might mean a null or something like that. But I can clearly state where I'm going to go given some state, some input symbol. I might go to multiple places, right? These might be sets of states. And I might get to go somewhere for free. Whoa, sorry about that. I might get to go somewhere for free because of this epsilon. But all of those are good things. That's amazing. So that is the recap between DFAs and NFAs. And then what we're going to find, first off, is that every DFA, by definition, can be called an NFA. And then what we're going to find is that we can produce any DFA using a special subset construction. And that'll be the topic for another video. So until next time, be kind to yourselves, be kind to each other. And of course, in order to be kind to each other, you have to be kind to yourself. I'll see you all.